Hello, everyone. Thanks for joining us today. I'm happy to be back again with another quantum-related talk. Today, we are very lucky to have Mohamed with us. He's a researcher at University of Waterloo as well as Vector Institute. And we are very fortunate to have him with us today to talk about his very interesting work. I really enjoyed reading the work. And hopefully you enjoy it too. So just a very quick bio of Mohamed. He's a student at Vector Institute and University of Waterloo, as I said. He works at the intersection of quantum physics and machine learning, and his main research interest is to leverage the tools that are commonly used in natural language processing with the purpose of simulating quantum systems. That's, kind of the overlap of two things that I really love. So I'm really excited to go through this work with him today. Just to give everyone a quick overview of what the work is about, I'll try to motivate it a bit before we start. So essentially, the work is based on using RNNs, recurrent neural networks, which are sequence-based architectures, very commonly used in natural language processing tasks. And what they are doing with it, what Mohamed is doing with it, is that they're trying to use RNNs to simulate physical systems that are sequence or lattice-like. And we get into more details about that. And they use, variational principles to train these models and, get, the wave functions and quantum states of systems like that. And they use the autoregressive nature of RNNs and similar methods like LSTM and GRUs to provide estimates of the different observables about the physical system. And they use it, for example, to calculate what the ground state energy is going to be approximately, the correlation functions, the entanglement entropies, and they do this for 1D and 2D systems. I was researching their work and I saw this paper that is citing their work that I read what they say about it, just so that you have an idea of what they did. So the citation says wave functions and other neural network representations of quantum state based on autoregressive models allow for uncorrelated sampling from the wave function, unlike traditional variational Monte Carlo methods, where an expensive Markov chain introduces potential biases in the calculation of observables and during the optimization of the quantum state. And they give, they go on to give two examples of methods like that, one of which is Mohamed's work. And this is from the paper called Machine Learning for Quantum Matter. And if you want to check that out, it is in the section called Neural Network Quantum States and their applications. Okay, with that intro, hopefully everyone is warm enough to get into it. So let's go through.
Thanks very much.
Yeah, of course. Let's go through some concepts, Mohamed, first to make sure that everyone is on the same page about what we're talking about. What you're looking at here is, a study of quantum many-body systems using, tools that are commonly used in natural language processing, like sequence models. Can you give us an understanding of what you mean by quantum many-body systems?
Yeah, so first, hello, everyone. Thanks very much for the kind introduction. Appreciate it. So basically, our goal is to, as you said, is to use the tools of natural language processing to simulate quantum many-body systems. And so basically, the main point here is that a quantum many-body system can think of it as a system with many particles that are based on the laws of quantum mechanics. So basically, quantum mechanics is a probabilistic theory where basically if you have a particle or a magnet that can point either up or down, there's not only a possibility of either having a spin up or like a magnet pointing up or pointing down. It can be a superposition of both up and down at the same time. And here, what we mean by a quantum many-body system, it's actually having a lot of these quantum particles that can have lots of interesting phenomena happening, and that also happens in times in nature at very small scales.
Perfect. Thank you so much for that.
Yeah, appreciate it.
And specifically, what you're using here is the spin system. Can you very briefly tell us what spin is for those who are not familiar and what a spin system means?
Yeah, thanks for asking. Yeah, so as I mentioned earlier, so what I meant by quantum magnet is actually a spin. So a spin is actually what I mean is a quantum magnet that can either point up or down. So those are very simple, quantum systems that are very easy to understand, and they serve as a very interesting toy model for theoretical and numerical methods. That's the main reason why we use them in this work.
Perfect. So I guess to sort of rephrase what you said, the spin is a property of matter in general that essentially, when in some systems, in some material, alignment of this property can result in magnetization, like we have in magnets.
Exactly.
And that's a very interesting toy problem for a lot of physical simulations, like what you're doing here. And
Exactly.
typically, the study of systems like that is done using density matrix renormalization group. I know that's a whole separate talk or multiple talks to talk about what that is, but just super high level, can you give us an understanding of what that is?
Well, yeah. So what's interesting about quantum systems is that they suffer from what from what's called the curse of dimensionality that I'm going to use in this talk. So this curse of dimensionality makes it very hard to simulate those systems exactly. And the goal of this density matrix renormalization is to go around this curse of dimensionality by approximating by trying to simulate those systems approximatively. So it's basically a variational method that tries to approximate the state of those quantum systems in a very efficient way without having an exponential cost. Right.
So essentially, if you try to solve the state of a quantum system, because of the fact that the size of the space that you're dealing with grows exponentially as a function of the number of dimensions, as a function of the number of particles, you can easily get divergence, and renormalization is a trick that you use to counteract that and get a good estimate of the state of the system without ending up with divergent solutions. And you mentioned variational methods. So I know that you use variational principles to train your RNN. Again, like very high level, can you tell us what you mean by variational methods?
Yeah, exactly. So for instance, in machine learning, the reason why we use neural networks is that they allow us to go around the curse of dimensionality of the huge search space in data. So they're used parametric model in order to find the minimum of a certain cost function. And in this work, we use what we call the variational principle, or basically the search space of the quantum system is exponential. In order to go around it, we parameterize those states using a certain model. Here we use recurrent neural networks. And basically the goal is to minimize the energy of the system so that you can have in a tractable cost without introducing some inefficiency in the calculations.
Perfect. And the ultimate goal here is to find the quantum wave function. Can you tell us very quickly and briefly what the quantum wave function is?
So one of the main assumptions of quantum mechanics is that every quantum system is fully described by what we call the wave function. But that's a wave function is a vector that has exponential size in the number of quantum particles you have in your system, for instance, spins. And basically, that's what we call the quantum wave function. And what's interesting about this wave function is that if you take the module squared, it defines a probability distribution. So this is saying that, like, so at very small scales in quantum physics, like matter behave probabilistically instead of like having either being 100% sure that this configuration happens. You have a lot of possible configuration that happens, and the probabilities of these configurations is associated with this wave function that describe this. That we assume that fully describes our system.
Perfect. And you kind of answered the next concept I wanted to go through, which is, the difference between a classical probability distribution and quantum probability distribution. And the difference is that, in quantum, when you're dealing with a wave function, it's a complex thing, not,
Exactly,
complicated, but, imaginary numbers kind of thing.
Yeah.
And, as you're estimating, here with your RNN, you're estimating the wave function. You're not estimating the probability like we're doing in NLP.
Exactly.
And right. And I think we've covered everything pretty much. I think there are two more concepts that I'd like to go through before we go to your presentation. The first is Hamiltonian. So what do you mean by Hamiltonian?
Yeah, so that's something I'm going also to talk about during the talk. So it's basically another ingredient of quantum mechanics, where basically, so every quantum mechanical system, we assume that it's fully described by this Hamiltonian. So this Hamiltonian serves as a way to describe the interactions between, like, for instance, spins within the system. And this Hamiltonian is in a form, you can see it as a matrix that has exponential size. So you can see, like all you need to know is that every system is fully described by a well-defined Hamiltonian H.
Perfect. And very briefly, I guess to rephrase what you said, Hamiltonian, again, is, as you said, an ingredient of quantum mechanics. It sort of represents the energy of the system.
Exactly, so you can use it, yeah.
Right. If I want to make
go
a very loose analogy, it would be similar kind of to the energy landscape or the loss function in, the typical, machine learning problems that we deal with. It's just essentially in some space, if you want to loosely think about it, it has a bunch of, valleys and, troughs, and your goal is to find the minimum of this landscape.
Yeah, I can see it like this is the classical way of seeing it. Definitely. Although, like in quantum realm, it's a bit different, but yeah, it's almost pretty much the same idea we're trying to do here.
Perfect. And last concept, I saw that you use a soft sign activation function. I wasn't personally familiar with it, so I thought maybe other people need a refresher on that as well. So just very quickly say what is it and why are you using soft sign?
Yeah, so like as I mentioned, or as you mentioned earlier, the wave function is complex valued. So you can actually decompose, like, since the wave function, the module squared of the wave function is a probability, you can decompose the wave function as like the module, which is the square root of probability times the phase term. So in our, like with our RNN, what we do is we approximate the probability with a softmax activation that's normalized to 1. And the phase term, we use like the soft sign activation function, which is like between -1 and 1, and we multiply that by pi so that the phase is between -pi and pi. So just a convenient way to parameterize the phase and to have a convenient way to write the complex valued wave function.
All right.
And we call these architectures a complex RNN.
That sounds great. Awesome. All right. That's all the concepts I wanted to go through with you before we go through the talk. So please go on and go on with the presentation. We have a bit of a trouble with your connection, so maybe if you don't mind, turn off your video as you're doing the presentation, and then we can turn it on when we get to the discussions. All right, okay. It's all yours.
Okay, thanks very much, Amir. So today it's my great pleasure to talk to you about a very recent work at the intersection of natural language processing and quantum physics. So this is joint work with my collaborators, Martin, Lauren, Juan, and Roger, who all deserve a lot of credit for this work. And this paper, this talk will be mainly an overview over the main results of this paper, which was published recently this year. So since this talk is intended to a non-physicist audience, I think a good place to start is with the great impact that quantum physics has made on our world during the last century and also during this century. So for those who are not specialists, as I mentioned earlier, so quantum physics is a theory that aims to explain the behavior of matter at very small scales. And inventions like LED light bulbs, MRI machine scans, and lasers are actually byproducts of our understanding of the theory of quantum physics. And what's more interesting about this theory is that it has a lot of potential applications in the future. And my favorite example is quantum computers. So those computers are actually based on the laws of quantum physics. And there is a lot of theoretical and experimental findings suggesting that those computers can outperform our conventional supercomputers. Hence they can advance science in many interesting ways. But the problem is that those computers are very hard to control, and research all around the world only managed to build very small blocks of these computers. And my other favorite example is superconductors. So those materials establish very interesting effects. So the first one is the ability to conduct electricity with zero resistance. And the other one is the ability to levitate on the air, as you see here on this picture. But the problem is here, in order to have those effects, you need to cool this material to very small temperatures, namely something like -100 degrees Celsius or even less. And now, the hope is and the question is there such a material that exists at room temperature so that, for instance, you can have cables that conducts electricity with zero resistance, since that would save a lot of energy. And for instance, why not having a car that can levitate on the streets if you have superconductor on room temperature? So we're not there yet. And all I'm saying here is that by those examples I mentioned is that there is still a lot of gaps in our understanding of quantum systems. In my opinion, the main reason of this is related to what we call the curse of dimensionality. So for those who are not very familiar with this idea, we can take the example of this simple quantum mechanical system made of quantum magnets, as I mentioned earlier. So in quantum physics, those are called spins that can either point down or up. And as I mentioned earlier, an important ingredient of quantum mechanics is called the wave function, which is a complex valued vector that has size 2 to the n. So 2 to the n here is the number of possible configurations that you can have using these spins. If you have n of them, that would make 2 to the n possible configuration. And here, the probability, if you take the modulo square of the wave function, that would define a probability distribution. So for instance, the first term here would correspond to the probability distribution, the probability of having this configuration occurring on reality. But the problem is here that the number of these configurations is exponential. So it becomes very hard to simulate such systems on a computer. And just to give you an idea, if you pick this specific number, then this 10 to the n would be like the number of the atoms in our known universe. Of course, that's beyond what we can do in practice. That's why the goal of this presentation is to show you how we can go around this curse of dimensionality by using the tools of deep learning. So in particular, I'm going to show you how we can use a specific tools from natural language processing called recurrent neural networks in order to approximate quantum mechanical wave functions, in particular, a certain class called ground states. So for this end, in the first of this talk, I'm going to show you how we can use neural networks for the purpose of approximating a specific class of wave functions known as ground states. And in the second part, I'm going to show you how we can use RNNs for this purpose. And in the last part, we're going to see how RNNs perform certain benchmarks of quantum systems in 1D and 2D, as published recently in this paper. Okay, so let's start. So in this section here, we're going to see how we can use neural networks for the purpose of approximating these a class of states known as ground states. Before I explain what this means, let me explain again what's the meaning of this Hamiltonian. So as I mentioned earlier, every quantum mechanical system is fully described by what we call the Hamiltonian, which you can think of as a matrix that has size 2 to the n by 2 to the n. And this matrix allows us to understand the energy interactions between spins in the system. And later on in the talk, I'll show you an example for how this looks like on a simple benchmark, on a simple model. So why this Hamiltonian is important? Because it allows us to define what the ground state problem is. So the ground state problem is basically an eigenvalue equation where you have a Hamiltonian, where the goal is to find the lowest energy, the lowest eigenvalue of the Hamiltonian H that you can interpret physically as the lowest energy of the system described by the Hamiltonian H. And the associated eigenvector is what we call the ground state wave function. That's a priori complex valued vector that has size 2 to the n. Now you might ask the question, why do we need those ground states? Well, it turns out that many interesting phenomena in nature happens at these ground states. So as I mentioned earlier, there is superconductivity. There's also an interesting effect called superfluidity, which is the ability of a fluid to have zero viscosity. And those ground states are also relevant in the context of molecular interactions, which is important in just for the development of better drugs and also better catalysts for fast chemical reactions. And it's also relevant in the context of optimization problems, where often the goal is to find the ground state or the optimal configuration that minimizes a certain cost function, such as in the case of the traveling salesman problem or in the case of the protein folding problem. So now, in order to find our ground state energy of this, or the lowest eigenvalue of the Hamiltonian, then a naive way to do this is using diagonalization, and then by picking the lower eigenvalue of the system, which is going to be our ground state energy. But now the problem is that since the size of the matrix is exponential, then using a typical algorithm, the complexity will be exponential in the system size, and basically by taking a relatively small value for n, then the complexity is almost the number of the atoms in our known universe. So that's of course not practical at all. So in order to go around this limitation, we map this eigenvalue problem to an optimization problem. So by taking our eigenvalue equation, we can rewrite it by multiplying both sides by psi dagger, and using the fact that psi dagger psi is normalized to 1, since we said that the module squared of the wave function is a probability distribution, and we get this expression. So since EG is the lowest eigenvalue in psi, we don't know what psi g is, we can rewrite this as the minimum over all the possible states that are normalized to 1. But here also, since the search space here is pretty huge, since the size of the wave function is exponential, we can go over this by introducing a parametric wave function, psi lambda. And here all we need to do is to minimize this, what we can consider as a cost function over the parameters lambda, in order to find a good approximation of our ground state energy. So basically here our goal is to choose a parametric function that's expressive enough in order to approximate our ground state, our true ground state of our Hamiltonian. And the more expressive it is, the more accurate this estimation of our true ground state energy. And because we want our wave function to be very expressive, we choose neural networks for this goal. That was what's the motivation of in this paper here. So basically, you can think of this neural network as a black box with some parameters metaphorically denoted by these knobs here that takes some input and gives you an output. And you can think of this neural network as a feed-forward neural network or a restricted Boltzmann machine, or as we're going to see in this talk, as a recurrent neural network. And the goal here is to minimize loss function by starting from initial parameters and then ending up at a good minimum of this cost function that would be a good approximation of our true ground state energy of our system. Now the question is, how can we estimate the energy or this cost, or what we call the variational energy or the cost function? Well, if you decompose this expression in terms of its components, as you see here, which you can interpret as the possible configurations of the system, as you see here, then you see that this sum here is exponentially expensive in n. Of course, it's very hard to implement that in practice, but what's interesting here is that you can see this sum. You see that this sum is a probability times another factor, and we can actually approximate that using what we call importance sampling, where all we need to do is to get the relevant configurations that have the highest probabilities from psi lambda squared, and that would allow us to have a good approximation. Also, an important note to make here is that we don't need any data within this approach. All we need, because all the data we get are actually from this wave probability distribution psi squared. So this is somehow similar, but not quite to what we do in reinforcement learning, where we also don't need any data in advance, external data in advance. And now the question is, how can we get those configurations, or how can we do importance sampling? And that would be the goal of this next part, where I'm going to show you how we can do this with recurrent neural networks. So as you might know already, recurrent neural networks are very essential components of natural language processing. So those architectures are known in theory to be universal approximators of sequential data, and they have played an essential role in technologies like speech recognition and machine translation. And what's more interesting about these architectures is that they allow us to perform a very interesting way to do importance sampling called autoregressive sampling. To understand how do we do this with RNNs, let us take this simple RNN cell that I'm going to define in a second. And we're going to initialize with this RNN cell with some initial vector h0 that you can think of as a null vector. And after we feed this initial vector, we get an output h1 that I'm going to also define in a second. And using this vector h1, we can define a probability p sigma 1. And using this probability, we can sample or flip a coin according to this probability to get either spin up or spin down. So for instance, here we get spin up. And what we do next is we feed that spin again to the same RNN cell. That's why it's called recurrent neural network, because it keeps occurring at each time step. And we feed in also the vector h1 to get a new vector h2. So this vector is calculated using this simple recursion relation. So there are more advanced recursion relations, but here I'm using the simplest one for in the case of vanilla RNNs. So here what we do is we concatenate this vector h and input sigma, and we multiply with a matrix plus a bias along with a nonlinear activation function to get the new hidden states. So since here we feed in information about the previous spins, then we call this vector a memory state. And we use it to predict the conditional probability of getting, in this case, the second spin conditioned on the first spin using the softmax activation. And then we just have to sample again to get the second spin. And as a note here, the parameters of the RNN would be the matrices W and U, and also the biases B and C. And all we need to do is just to repeat this procedure many times until we get our full spin configuration, whose probability is just the product of the conditional probabilities according to the chain rule, in which we can interpret as the module squared of what we can call the RNN wave function. And interestingly enough, by repeating this procedure many times, by getting many of these configurations, we can have a good approximation of our variational energy given by our RNN. And basically here, all we need to do is to optimize our RNN by RNN parameters, metaphorically denoted by this knob here. So all you need is just to run lots of gradient descent steps until reaching convergence where we expect to have a good approximation of our ground state energy of the system we're studying. So to illustrate all of this on a concrete example, let us see how we can use RNNs to study one-dimensional quantum systems. So a very interesting toy model to look at is what we call the Quantumeisen model in 1D. So you can think of this model as a one-dimensional chain of spins. It can either point up or down. And in this chain, there's two types of coupling. There's a ferromagnetic coupling that encourages spins to align either up or down. And there's also a spin flip coupling that encourages every spin to flip. So in some sense, this first coupling encourages the configurations to be ordered, and this second term encourages disorder in the configurations. And this is encoded in a nice way in this Hamiltonian. So you don't need to understand all the details here. All you need to know is just the first term corresponds to the ferromagnetic coupling, which encourages order, and the second term corresponds to the spin flip coupling, which encourages disorder. And if you would like to write this as a matrix, for instance, if you have two spins, this would look something like that. But since, as I told you, since the size of the matrix is exponential in n, then it's more, using this notation is more compact. And here, since there is a composition between order and disorder within the system, then the lowest energy state, or the ground state, would not be only made of ordered configurations such as those with all spins up or all spins down, but it will be also like a combination between those states and also disordered states. So in order to minimize the energy, then it will be a superposition of many of these configurations. And the goal is to use an RNN in order to have a good approximation of the ground state and the ground state energy of this system. And that's what we do here using for 1,000 spins. So that's something we can do with exact diagonalization, as I mentioned earlier. And what's interesting about this model is that we can know what the exact energy is. That's what makes this model a very good benchmark for this method. And what we see here is that by taking more gradient descent steps, we see that we actually, the relative error, which is the difference between the RNN energy and the exact energy, is going down to very good accuracies, which allows us to have good approximations of the ground state energy of this model. So that was a very positive benchmark on here, on this model. Now, the question is, how can we use the same idea to study two-dimensional quantum systems? So as you might know already, one-dimensional recurrent neural networks are inherently one-dimensional. They're mostly suited to study one-dimensional structures such as a sentence, words in a sentence, or like, as I told you before, a chain of spins. In order to generalize this to these systems, instead we use two-dimensional recurrent neural networks, where instead of using a one-dimensional recursion relation where you only have a one memory state, we actually use two memory states. One that's horizontal and the other is vertical. That allows us to account for the 2D geometry of our system we're interested in. And in order to sample configurations, we use a zigzag path which is autoregressive, and we just follow these red arrows to generate our 2D configurations. And this would look something like that in practice, if you would like to do it on a concrete example. So to illustrate that, the power of this architecture, we use the same model, but now in 2D, where you have the same types of coupling. You have a ferromagnetic coupling, which encourages order. So every two neighbors, this coupling encourages the spins to align either up or down. And you have also another coupling which encourages disorder. And what's interesting about this model in 2D is that the ground state energy is not known theoretically. So using this method would allow, and such methods based on this principle would allow us to go beyond what we can know in theory. And here we benchmark this model on Hamiltonian, on this model with system size 12 by 12. That's something, as I mentioned, we can't do with exact diagnosation. And here we compare with two state-of-the-art methods. So as I meant, like as we talked about earlier, we compare with DMRG and pixel CNN. So those methods also are based on the variational principle that where you introduce a parametric wave function to find the ground state energy. And it's, for instance, if you look at this panel here for this value of disorder H here, then like you see that the RNN finds a lower energy compared to the others, meaning that we have a more accurate estimation of the ground state energy of this model. And what's more interesting is that RNNs are actually more compact. So for instance, we can find competitive results using almost 4 orders of magnitude less parameters compared to DMRG, and almost 2 orders of magnitude less parameters compared to the pixel CNN. So I think that's pretty much all I wanted to talk about today. So my main takeaways from this talk is that first, we can use the tools of natural language processing not only for applications like machine translation and speech recognition, but also to study quantum mechanical systems. And second, we can use RNN wave functions to go over the curse of dimensionality in slightly large system sizes. And also, in this talk, we have seen that RNN wave functions are competitive with the state-of-the-art methods in 2D. And I think my main takeaway from this talk is that the future of the interplay between neural networks and quantum physics is really promising. I think there's a lot of interesting work we can do in the future. So that's pretty much all I wanted to say today. Thanks very much for your attention, and I'll be happy to answer your questions. Thank you.
Awesome. Thank you so much.
Thank you.
Let's get into some discussions.
Sure. Yeah.
So first, there are a couple of questions from the audience. I'm going to ask those first, then we can get into the questions that I prepared. If you don't mind, try turning on your video, and hopefully that works. If it doesn't, I'll let you know, and we can turn it off again.
Yeah, so I'm trying.
Okay.
Yeah, maybe there's an issue with the video.
Oh. Okay, don't worry about it.
Okay, sorry.
That's all good. Okay, so the first question is, since you're using soft sign,
Yeah.
is there any?
Yeah, finally it's not working. Can you see me now?
Yes, it does.
Oh, cool. Thanks.
Okay, so the first question is, since you're using soft sign, is there any concern about the divergence of the problem? Because in soft sign, you go from -1 to 1, which are different values, but phase, minus pi and pi are almost equal values for all intents and purposes.
Yeah, that's a very good question. So if we go back to the slides here, so something I didn't mention during the talk is how, do we express this this term here, which we call the local energy. The local energy is something that looks something like that, and here we need to have an expression for the wave function for a certain configuration sigma. And as I mentioned earlier, psi lambda of sigma, you can write it as a square root of probability distribution times a phase term. And here we use phi times a soft sign activation function. So here, when we're training, when we get the relevant configurations from psi squared, the phase term will disappear, because then psi squared will be just a probability distribution, and then here what's relevant is this probability, and we only need the soft sign to estimate this term here, but during the sampling procedure we don't need those phases. And actually, it's actually during the sampling procedure where this we don't have an instability because of this soft sign, because here everything is smooth and works fine.
Okay.
I hope
So,
that helps.
yeah, I mean, that was my understanding too, that essentially the overall phase doesn't matter. What matters is the relative phase of, consecutive terms. And, that is something that is built into your process anyway. And that should be completely fine the way you're treating it. And Aisheng has another question that is asking, in principle, in your process, you're generating multiple, potential wave functions, and then use that to calculate, essentially the energy. So that could give you many different energies. So is there any situation where you end up in, degenerate situations where you have multiple wave functions with the minimum energy that is possible as your solution?
Yeah, that's a very good question. Yeah, like this is something I didn't talk about during the talk. So for the models I've mentioned in the presentation, the ground state is not degenerate. So meaning that there's only one minimum. Like a priori, like we don't have problems with like in local minima. So when we do optimization, we go straight to the ground state. Mainly, my understanding of it is that there is not a lot of degenerates, and also there's not like a lot of local minima on the way. But so if you have degenerate ground states, one way to go around this is to use symmetries of the problem. So it turns out that like those degenerate ground states have some certain symmetries. So for instance, you can have a wave like a state that have parity symmetry, and the other like you can use those properties to target a certain ground state, and then you can with this you can study a lot of the properties of degenerate ground states. But that's something we didn't try yet. I think that's something interesting to look at in the future.
Definitely. And I guess like I'm going to try to regurgitate what you say to see that I understood. So in most cases that you dealt with, the minimum energy that you will end up with is given by one wave function, and that's what your optimization does essentially.
Exactly.
It is true that along the way you generate a lot of wave functions, but most of those are not your ground states. Those are just essentially your samplings that you use to find your path and gradient to the global minimum that is your ground state.
Exactly. Yeah. You can see it this way as well. Yeah.
Awesome. All right. So, audience, if you have questions, please put it in the live chat on YouTube, and I'm happy to relay them. But in the meantime, I'm gonna, throw a bunch of questions at you, and hopefully we can discuss those.
Sure.
So, one of the things that took me a while to understand, coming from the more machine learning side of things these days, was the training of your RNN. Because in natural language processing, when we use RNNs, we throw a bunch of data at it, and we train it, and it is for a particular task. But here, what you told me was that you don't really have that kind of training that requires data. And I know you mentioned in your presentation, but maybe you can talk a little more about that process, like how does it work?
Yeah, that's a good point, because like that's where it gets a lot of confusion, because like natural language processing is mainly used in like you use external data, but here what we are doing is we're using let me go back to the relevant slide before. So yeah, it was this one here. So basically here, what we're doing is we're getting the configurations that have the highest probabilities from this well-defined wave function that have some parameters. So having a given parameters, lambda, allows us to define this quantity here, this probability distribution we can sample from using, for instance, an RNN wave function here, as you see here. And something to mention as well is that so in order for in the beginning when we start training, so the parameters of the RNN here are actually initialized to random values, And also this initial hit, like vector H0 is also initialized to a null vector. And this allows us to have, like just to start from, like this, using this, we can, starting from this, we can run a couple of gradient descent steps in order to achieve a global minimum of our like energy landscape, and that where we expect to have a good approximation of the ground states. And I hope that clarifies a bit the difference between this and natural language processing. Yeah, and also one interesting difference with natural language processing is that here, instead of like in natural language processing, here we're sampling actually words, but instead here we're sampling spins.
Right.
Also, like one fundamental difference between what we're doing here in natural language processing, and like what's more interesting here is that like for spins we only have two possibilities, but for words like it might happen that we have like 10,000 or a lot of them. But
Okay, perfect.
it's a lot easier because you only have two possibilities.
Makes sense. Awesome. So, Aisheng is following up with another question that is, do you have an intuition for why you are able to essentially simulate or estimate the ground state wave function using so few parameters in your RNN? Like, what is the sort of physical and or computational intuition of what is happening there?
Yeah, that's a very interesting question. That's something I didn't have time to go through. I think, yeah, that's a very interesting question to address. Let me see if I can go to relevant slide. So a very interesting observation in physics is that the low energy states actually lives in a small manifold. You can think of it as just like small space compared to the full space with 2 to the n possible of the possible wave function that have size 2 to the n. So this space is very small compared to the full space that we call a Hilbert space. And this has like the fact that those states have some structure that allows that makes those states live in a small subset of this Hilbert space allows us to use these models to approximate them. In some sense, this is similar to what we do in machine learning, where you can, for instance, embed images which live in a high dimensional space only in 2 dimensions. So you can think of it something like that here, where those low energy states, for instance, the ground state, have some structure that allows to introduce or to use models like RNNs to find an approximation of the ground state. In some sense, like this is something that we're lucky to have in nature, because otherwise it will be impossible to find such ground states if such states live in the full Hilbert space.
Right.
And one interesting thing that makes these, one comment here, what makes these systems also appealing or possible to study is the fact that they establish a lot of symmetries, such as translation invariance. But this is a very important, a very interesting result, that was done by a paper that was published after a work, where basically they show that RNNs are very good at studying systems that have a translation invariance. So what this plot shows is that, for instance, if you go from a system size 80 to 100, then if you, for instance, you train your RNN on a system size with 80 spins, then you want to go to 100 spins, then basically you only need few gradient steps to achieve the minimum. And if you do this for a larger system size, from this value to this value, then you need fewer mini batches or gradient descent steps. In some sense, those RNNs also encode the translation invariance of quantum systems, of those systems I mentioned earlier. So this is like my understanding of it. Of course, there might be other reasons. I think this is still an open question. Like nobody has a very clear answer about this.
Definitely. I'm glad you went through the translational variance because I saw it in some citing papers, but I wasn't quite sure how it translates. So that makes a lot of sense. And if I want to summarize what you said, essentially, the fact that you don't need many parameters is an inherent symmetry that the ground state wave functions of most physical systems have. So they're usually pretty simple, if you like, because of all the symmetries that they have. So essentially, the probability distribution lives on a manifold that you don't need a very large number of parameters to essentially parameterize. And that's why, regardless of what the Hamiltonian is in general, finding the ground state using few parameters is possible using RNN in this case, which, kind of, brings up another question for me, like, how would you use this architecture to get the, to get the wave function for the excited states?
Yeah, that's a good question as well. So all I mentioned, that's something I'm also trying to. I'm still an open area of research. So there's so all I presented today is how to use RNNs to approximate ground states. But in order to approximate excited states, you have to work a bit more. So what's interesting about those excited states, which correspond to eigenvalues of the Hamiltonian, is that they have well-defined symmetries. So for instance, if the ground state has parity, the first excited has the inverse parity. Or for instance, if the ground state is invariant under reflecting symmetry, then the other one have the anti-reflection symmetry. So if you embed or encode the symmetry in the RNN, you can target different excited states. So that's something I'm still it's still an open area of research. I'm still thinking about this way for doing. But yeah, I think it's a good question. It's good promising area of research.
I was keeping a question for the end, but I guess since we got to this point, I guess I can go there. In natural language, since you mentioned natural language processing as a way of getting inspiration for your work. In NLP, we have kind of moved on from RNN-based architectures since a few years ago to more transformer-like architectures, and I think a big part of that motivation of that transition was the fact that transformer architecture is a lot more parallel, and it allows you to calculate multiple variations of what the essentially multiple kernels, if you like, and then use those to calculate whatever property or probability distribution you're trying to predict. And based on what you're saying and based on the question that Aisheng asked, I feel like probably if you want to get to the higher excited state levels of excited state energies of your system, you probably need to go to higher capacity models and potentially and then there's the computational problem, and then maybe going to transformer architectures would be an interesting approach. I'm not sure. I'm just brainstorming kind of live, but what is your take on that? Like, is that something that you're thinking about?
Yeah, definitely. Yeah, I think transformers, as you mentioned, are very powerful in natural language processing, mainly because they allow to encode large, long-term dependencies between words. We can use the same idea to have long-term dependency or to encode long-term dependencies between spins, for instance, as we do here. So definitely, I think that's a very promising area of research. Although, there's a lot of so there are lots of advantages, as I mentioned. There's parallelizations, they're very quick if you have a lot of parallel computing, but those architectures takes a lot of memory. If you use the vanilla version of transformers, lately I heard about these linear transformers which have lower complexity. So maybe using those architectures allow us to have better performances compared to recurrent neural networks. So I think that's still an open area of research, mainly because RNNs have also the interesting property that they are very cheap in terms of computation, and they also established translation invariance. So maybe like borrowing properties from RNNs, like with these properties, and also from transformer would allow us to have more interesting architecture for studying quantum systems. And I've also came across this paper where they found a connection between RNNs and transformers. So they found that RNNs are transformers, and I think that's an interesting way to like a good place to start within this approach. But like I don't have very definite answers, to be honest. It's just it's also brainstorming as well. And so I think it's pretty much I think it's an open area for research. Yeah, and also one important thing is I also wanted to mention is that like so as a future direction, like I think using like quantum systems would be also a very good benchmark for RNNs and also other deep learning architectures. I think like because those systems are very clean, like you don't have any noise like in real world data, so you can have like a good sense to how good is your model or how expressive it is, depending on the accuracy you get or something like that. But that's just something for future work.
Definitely.
People are interested.
I would be also curious to know, like it just occurred to me, if there is any correlation between, your last item here and things like restricted Boltzmann machines, because in those also you are using spin systems to simulate the problem that you're dealing with. Anyway, so since we don't have a lot of time, I'll ask one more question from Aisheng. I'm just going to heavily rephrase what he's asking just to be more brief. So essentially what he's asking is, do you need to change anything about your architecture, about your RNN architecture, depending on the symmetries that your Hamiltonian has? Or is that like an independent consideration?
Yeah, that's a good, important point. Yeah, so I think definitely dependent on, I would rather say the geometry of the problem, then like you need to change the architecture of the RNN. So as I mentioned during the talk, if you have a one-dimensional system, then using a conventional RNN would be good. So in 2D, we found that it's better to use a two-dimensional RNN. We have like a two-dimensional recursion relation. Now, if you have a graph, then it would be better to use like something like a graph or recurrent neural network for this. Indeed, like encoding the geometry of the system would be very helpful because you're kind of having some inductive bias, or you're introducing some physical information about your like architecture. But also something interesting to that would also help is that, for instance, if you don't have translation invariance, it would be better to use different parameters in each RNN at each step. So, like in natural language processing, we use like parameter sharing over all the time steps. But if you, for instance, you don't have translation invariance, it would be much better. That's something I also noticed during my numerical tests, is that if you use different parameters at each time step or at each site, then you get optimal parameters. So you can using symmetries and ideas about the Hamiltonian, which definitely help to get better results.
Perfect.
Hope that's most helpful.
Definitely. I think just a side note from his question, I think he was also interested to know if you keep the dimensionality the same and keep the dimensionality the same, but change the symmetry. Like, for example, if you go from ferromagnetic, Hamiltonian to an anti-ferromagnetic Hamiltonian, like, would that change anything about your architecture? If you can do that in like 30 seconds so that we can wrap up since we're out of time.
Yeah, so I think also that's also an experimental question. Like if you have anti-ferromagnetic, you can also use like an alternating RNN, like one for spins up and one for down. Like you can alternate RNN1, RNN2, RNN1, something like that.
Right.
That's something how I see it in my mind, but it could be something else for the works better.
Definitely. Awesome. Thank you so much, Mohammed. Appreciate sharing your findings with us. Just quickly to wrap it up, I'm going to go through the takeaways from this work. So essentially, you used recurrent neural networks to do an autoregressive model to find the ground state of certain spin systems. You tried this out on one-dimensional and two-dimensional systems and saw a very good performance compared to other alternative approaches like pure variational Markov models, Monte Carlo models. And one way to think about it, like why autoregression is working here, is that you start from, say, one corner of the system and autoregressively just learn what the ground state should be throughout the rest of the system. And it's very interesting that you don't need data to train this model. You're just using the properties of your Hamiltonian to provide the feedback to your system.
Yeah.
And you use that to calculate what the energies of the ground state would be, what the correlation functions would be, and things like even entanglement entropies, since you already have an estimate of the ground state wave function. That's very interesting work. I'm glad that we got to talk about it today. Thank you again for joining us and sharing your research. I know Reza was on the call as well. He was going to ask questions, but unfortunately he has some audio problems. So hopefully, we bring you back again, Mohammed, and next time Reza can also join us in the conversation. If you want to say any last words, or otherwise we wrap up the session.
Yeah, thanks very much, Amir. Appreciate it. Thank you.
Of course. Thanks again, our audience, for joining us today and all the questions. Please go to ai.science, create a free account to get notified about all the upcoming events. We have probably 3 to 5 events every week, 5 sessions like this, and a lot of social sessions as well. Thank you again, and see you next time.